All right. So a sample contains 1 gram of radium. How much radium will remain after 1,000 years, given its half-life is 1,620 years? So we need to find the rate that it's decaying. Okay, so you've done these before. Let's just say half-life means whatever you had at the end of that half-life, you have half of it, right? And we know this formula, and well, you don't know because I didn't go through the PowerPoint with you, but y equals the constant times the e raised to the RT. You have totally seen that formula before, yes? Okay, C is that initial amount, y is the new amount. So let's pretend we already said it, 1 gram of radium. What would half of 1 gram be? 0.5. E, don't know the rate of decay, but to get to half of it, it took how many years? 1,620. Okay, so how do I solve for R? First, we do what to both sides? The ln, so we're going to rewrite this as the natural log of 0.5 equals, you actually would have divided by 1 first, but 0.5 divided by 1 is 0.5, right? And then the natural log of E goes away, so now you have what? So can I write it as 1620R? It just makes me feel uncomfortable when I put the number in front of the variable. And then I'm going to divide by that 1620, yes? So there's my rate. It's the natural log of 0.5 divided by 1620. Now when you punch that, get out your calculators. When you punch that in your calculators, it's going to be, I'm assuming a decimal, it keeps on going. And you don't ever want to round because we haven't answered the question. How much radium will remain after 1,000 years? So you just want to keep that as your rate. So then when I go to answer the question, how much radium do I have when I take 1 gram at e raised to the rate that I just found? And you guys probably remember me doing this before. I'm just going to call that natural. It's e raised to the, if you wanted to, you could redefine, I think I did like smiley face or something like that, or I could write it in. Okay, so I know this is smiley face, so then e raised to the smiley face times how many years now? No. 1,000 years. So what I'm going to do is I'm just going to go to my calculator and I'm going to first type in smiley face, which is the natural log of 1/2 divided by 1620. And then I'm going to multiply it by 1,000. And then I'm going to take e raised to that answer, and I don't even need to waste my time multiplying by 1. What are we getting, guys? How many grams do we have? 0.652 grams. You're feeling good about that one? You're like, oh my gosh, this is great, Mr. Dice. Good. I'm glad you guys, easiest thing you've done all year? Okay, careful. Just careful there. We're doing 5. Experimental population of fruit flies increases according to the laws of exponential growth. If there are 100 flies after the second day, everybody do this for me. I'm going to help you out here for time. After 2 days, I have 100 fruit flies. And after the second day, and 300 fruit flies after the 4th day. So after day 4, I have 300 fruit flies. That's probably going to come in to help me somewhere. That's just my guess. Okay? How many flies were in the original population? So I'm asking for C. So we're asking for C. Well, if I think about it, let's what's that now?
So you do y over e to the RT.
Y over. Okay, so C equals Y over e to the RT. Okay, but I don't know. I gotta do that in relation to a couple things first, Cam. Okay, you gotta get your rate. So I know this. I did know this. I knew that after 100 or I had 100 fruit flies, right? That was my. So I don't know my initial value C. E raised to the, and here's what you gotta do. 2R. Agree? So how about C equals 100 over E to the 2R? Would you agree with that? Yeah? Okay. And then I can, for sake of time, then we can go with this, plug it back in, use the other value here, because I gotta get to the new Newton's law of cooling, sorry. Here, to work backwards to find the C, okay? I want to go to the back side, which is the brand new stuff, okay? So, if I need, here, let me give you the answers. Let me give you the answers. C should have been 100 over 3. And number 6 down here at the bottom, you should have gotten 11.552%. I want you to finish those two work problems on your own, and if I need to come back and show you next class, we can. We'll have normal day next week. I want to go to the back side, and this is where Newton's law of cooling occurs. Okay. A bottle of soda at room temperature, set in our room temperature 72 degrees Fahrenheit, is placed in a refrigerator where the temperature is 44 degrees, so the refrigerator is 44 degrees. After half an hour, the soda is cooled to 61 degrees Fahrenheit. So that's giving me information that allows me to find what is the temperature after another half an hour, and this is where we're going to do Newton's law of cooling. Okay, so what you do is, here's what we do. Y equals, what we originally have the temperature of what is where our thing, in this case soda pop, is being cooled at. What's the temperature of where it's being cooled? Not what the temperature of the soda can is. The refrigerator is 44 degrees, so it's 44 plus the C times E, and I like to use K, T. K is R, so if you want to use R, that's fine. I just like with the Newton's law of cooling, we use that K. Okay, there's a lot of background information how this was derived. It is, if you look in your textbook, it shows you how they came about that formula. Okay, so what we want to do is, after half an hour, the soda is 61 degrees. Okay? So the soda is 61 degrees. But what I first need to do is I need to find that constant of cooling at time 0. We need to find C first, excuse me. We need to find C first, what you don't know. But here's what you do know. At time 0, what's my soda can? 72 degrees. So that's how we go about finding that C. So we're going to say, before we even put it in there, 72 equals 44 plus C e to the, and think about it, at time 0, this just becomes e to the 0, which is 1. So we'll just put e to 0, so that's 1. So C would be equal to, what do we get for C then? 28. cool. So
What does
now,
that mean?
what's that?
What does that mean then? 28
The 28 allows me to go back in through here. Let me put the equation now for you, Cam. 44. It is the, here, can I grab my book and make sure I say it correctly? Okay. What was the section where I say 5.2? This is how he found this way, this method always allows me to solve for the cooling. So I don't know the technical what it is. But I do know now that y equals the 44, I think I started this, I never finished it, plus 28 e to the kt. We can find k now. After half an hour, the soda is 61 degrees. So what I'm going to do is I'm going to say the soda is 61, which is equal to the 44 plus 28 e to the kt. In this case, I want to make sure I put in the t right. Let's talk about it in minutes, right? So we're going to say 30k.
Why minutes?
Because I don't want to do it in terms of hours, because it's going to come out in minutes. I don't want to point, whatever. We're going to say this many minutes. You follow me? So 30k. You would not have been wrong if you did 0.5. Your answer would have been in terms of hours. Okay? So let's solve this. Everybody, let's solve for the k and see if you get the same thing as me. I'm going to subtract 44, divide by 28. So let's see. 61 minus 44 is what? 17? Divided by 28 equals e to the 30k. And then I'm going to take the natural log of both sides. So I now have the natural log of, in parentheses, 17 over 28 equals 30k. Do you all agree with that? So k, I'll come right here to the right, is equivalent to what the natural log of 17/28, close that parentheses, divided by 30. I don't even know what it is, and I don't care yet. Okay? It's something, right? And I know you all have it. I'm going to call it smiley face. Because now I have my constant of cooling. Now it's going to allow me to answer part A, because I haven't answered part A yet. What is the temperature after another half an hour? So how many minutes? 60. Or you could have used one. Either way, it would have came out right. So that equation to answer part A now would be y equals, what, 44 plus 28 e to the smiley face times 60. Let's all go to our calculators. Let's crunch it and let's see how we did. I feel like I don't have my answer in front of me.
I do that.
Yeah, sometimes the hardest part is just making sure we're crunching into our calculator correctly. I'm getting 54.321 degrees Fahrenheit.
Wait. You got 5, 4, 3, 2, 1 is the answer.
Oh, dude, you're right.
Oh, I didn't.
I was like, wait a minute.
I totally didn't get that. Well, that doesn't make sense, does it? That definitely doesn't make sense if we're trying to do Newton's law of cooling and now we have a... Do you know where you did wrong? Where, Eli, maybe? Voodoo math it? Are you guys getting that? No?
Whoa, what they're doing wrong. I totally got this right. I get it.
Did you get this first?
Yeah.
Times 60? E to that? Times 28?
The
plus
parentheses-
44.
Yeah, the parentheses need to be right. too.
Yeah, that's why a lot of you just work
Wait a minute.
inside out, just do it.
Wait a minute.
Quit doing all the parentheses.
Oh, yeah, there we go. I multiplied by 44.
Okay,
There we go.
alright, so then, B. How long does it take for the soda to cool to 50 degrees? So this time you know Y, you don't know T. So I would do B by saying I know what's Y? 50. When does 50 equal 44 plus our 28 that we found? That's a C of 0. So it's like the initial constant factor, Cam, something, I don't know, of E raised to the, I'm going to do smiley face again, and I'm solving for T. Let's see if you can do that one. Do you want to do this one together, Pipe? I'm going to hit pause. You should have gotten T, if you did not round early, 92.614. Now, there's our answer.
Yes.
We have time to do the other example. I think then we'll have the Newton's law of cooling locked in. So,
That's a minute.
huh?
That's a minute of the T.
Yeah. So we could. Yeah. So 92.614 minutes. So what? Hour and 32 point. However you want to think about it. All right. Let's go down here. Hard-boiled egg, 98 degrees Celsius, so it's obviously hot. It's put in a pan under running 18 degrees Celsius water to cool. Does anybody do that? Anybody boil eggs? We boil egg. We put it real hot, and then I always have a big bowl of ice water. Like I put a bunch of ice in it, and then so as soon as you get done boiling it, you put them in there and let it sit for like 5-10 minutes, and then they peel off effortlessly. All right, so we got the hard-boiled egg. We're going to put it in a pan under 18 degrees Celsius water to cool. So what that's saying is that water is not going to warm up. We're having that cold water just continuing running over that hard-boiled egg. Okay, you follow me on the Newton's law of cooling. After 5 minutes, the egg temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees Celsius? All right, let's write our formula and let's do this. Let's go Y equals, what's the temperature that we're using to cool our egg? 18 plus the C e to the k t. Everybody cool with that? We need to find that C, right? And how am I going to do that? We're going to say, what's the egg at time 0? 98 equals 18 plus C e to the, think about it, 0 times k is 0, e to the 0 is 1, C is 80. Y'all comfortable with that? So now we have the equation, Y equals 18 plus, what is it, 80 e to the kt. After 5 minutes, the egg temperature is 38. 38 equals 18 plus 80 e to the, what did I say that was, 5 minutes? So 5k. Subtract 18, 20 equals 80 e to the 5k. Divide by 80, simplify that, 20 over 80 would be what, 1/4? E to the 5k. How do I get to k? I bring what in the mix? ln. So now have the natural log of 1/4 or 0.25 equals 5k. Divide by 5. There's my k. Now that I know k, I can use, how much longer will it take the egg to reach 20? I'm going to use 20 as the y. So I'm going to say, when does 20 equal our 18 plus 80 e to the, we know k to be, I won't use smiley face this time, I'll actually write natural log of 1/4 divided by 5, yes? T. Go ahead and crunch, guys. And basically, you need to be just doing your calculator now and see if you can get it. I heard it. Well, whoever said it out there, I heard it. 13.305 seconds, but that's T. Technicality, how much longer?
Yeah, so you have to subtract.
It's already gone how many? 5 minutes? So how much longer would be just simply subtract 5, 8 minutes. 8.305 minutes.